Okay, so we're going to do the calculus part of this. One thing you've noticed so far is that there really is not a lot of extra stuff that involves calculus relative to the first part of the book, and that's just the way it is. Right now we're talking about work and energy. Work is basically the way that we can change energy from one form to another, or we actually used the definition of work to calculate what kinetic energy is. We also used the definition of work in terms of gravitational potential energy to calculate what potential energy is, which is the energy associated with the position of an object relative to another object associated with the force due to gravity. So in that particular case, for calculating gravitational potential energy, we took an object that had a weight W and we pushed against that weight to move it to a different height. And so the work done in moving that object through a distance h was equal to the force, which is the weight, times the length, which is h. And so we came up with the gravitational potential energy was equal to the mass of the object times g, which is the weight times the height of the object. And also when we calculated the spring potential energy, we said that when you compress or stretch a spring, that the force is proportional to the displacement. So from a calculus-based standpoint, we end up integrating this result. If we plotted force versus distance for a spring, it looks something like this. And so if we integrate it calculus-wise, we would just integrate x dx, which is x squared over 2. K is a constant, so they call it the spring constant. And so we found out the spring potential energy was 1/2 kx squared. And if you integrate from some initial state to some final state, then you insert the upper limits and insert the lower limits and subtract the initial conditions from the final conditions in this way. So the other way that you might use calculus is if the force as a function of distance were something other than either constant or linear, which is our two examples up to this point. Here was constant, here was linear. So what I've shown here is force versus distance. And from our labs, we've seen it looks something like this. So when you first start to push on it, you accelerate it, and then as your finger leaves it and you finally let go of it, then this is the force, and then the distance over which that happens. And so calculus tells us the area underneath this curve between the curve and the x-axis is the integral of f of x, which is this curve, times dx. So what I've come up with here is it kind of looks like a sine wave, but it's been shifted up. So if you, this is a function that would look like this. So you have the F max divided by 2. F max is the highest, the peak force. Then you have 1 plus the sign. This 1 is to shift it up away from the x-axis so that it oscillates like this instead of oscillating around the x-axis. Now the sine term is reasonably complicated, but what's involved here is that this delta x over 4 subtracted is to shift the function. If I didn't have delta x over 4, it would look like this, but I want the force to be 0 at x equals 0 instead of 1 at x equals 0. So that's what this does, is to shift the function delta x over 4, where delta x is the total displacement during the time the force is at it. So that's what that's in there for. And then this little bit is to make it so that when x equals, let's say when x equals 3/4 or half delta x over 2, when this is equal to delta x over 2, the delta x's cancel out, and you end up with the argument of the trig function being pi over 2, which will give you the peak occurring here halfway instead of a quarter of the way. So this is correct. I've initially I had it wrong, but I fixed it and I've come back now. So the work would be the integral from x equals 0 to x equals delta x. And the force as a function of displacement, as a function of x, is this equation. And you multiply the whole thing by dx. So this is a constant, so we can bring that outside the integral sign. The integral of 1 is x. So the integral of 1 dx is x. And if you integrate this function, you'd use substitution. And so you divide by this constant that's in front of this x and the little thing that shifts it. So you divide by this so you can multiply by the reciprocal. So you can see I multiplied by delta x, so they divide by 2 pi. The integral of the sine is negative the cosine. And then the argument stays the same. And then I evaluate the integral from x equals 0 to x equals delta x. So if I plug delta x in, I'll get delta x minus this cosine of 2 pi delta x over, and then I put delta x in for x. And then everything else is the same. Then you subtract the lower limit, so you put in 0 for x, and then you put in 0 for x here. Okay, so what will happen is you'll get 1 delta x minus a quarter delta x, which is 3/4 delta x. The delta x's cancel out. This delta x will cancel out with that delta x, so we're just left with 3/4. Down here, the same thing applies. This delta x cancels out with that, and then you have 2 divided by 4, which 2 over 4 is, this becomes a half, so you get negative pi over 2 here, and you get positive 3 pi over 2 up here. 6 times 3 is, 2 times 3 is 6. 6 divided by 4 can be simplified to 3/2. So what we want to do to evaluate this, we have to evaluate what the cosine is at 3 pi over 2 and the cosine at negative pi over 2. So you come down here and you draw a unit circle and you say, okay, the cosine of an angle is equal to the x-coordinate on a unit circle, and the sine is equal to the y-coordinate. So negative pi over 2 is here, and also positive 3 pi over 2. So they're going to have the same value. And the x-coordinate here is 0. The y-coordinate was negative 1. So this is 0, and this is 0. And so everything drops out except this term. So it turns out that the work done in pushing something where the force as a function of displacement is a sine wave is just equal to the maximum force divided by 2 times the displacement. If it was a constant force, then it would just be F times delta x, but it's a sine wave, it's half of that. So there's an example of some function, a little more complicated, where you calculate the work. Now the only other thing I'm going to talk about is it's mentioned in this chapter is if you want to take into account the fact that the force is not in the direction of the displacement, you have to use what's called the dot product. So we have that the work is not just the integral of f dx, or f dx. That's if they're in the same direction. But if you have to use a dot product. So dx is a vector, it's a dx vector, and the force is a vector. And it turns out that if you have a force vector in this direction, and let's say you want to, your displacement is in this direction, so we'll say the displacement dx vector is here, and this is my force vector, and there's an angle theta between the two. It turns out that the dot product, if you take f vector dot the dx vector, it just ends up being the force, which is a scalar, times the cosine of theta times just they actually call this DL, the DL vector. So when you do a dot product, it's the cosine of theta, and you kind of think of it, that would be like the x component. If I took the x component of the force and I multiplied it by the distance in the direction. And we kind of did that when we looked at a problem in class, I think. If we were pulling on an object, so from an algebra-based standpoint, if we had a block that's sitting on a surface, let's say it's frictionless, and you apply a force to pull it like this, and this thing is going to move in this direction. From an algebra-based standpoint, what we do is we break this up into two components. And this is our angle theta. This would be f sub y, and this would be f sub x. This would be f. So all we do there is we say that the work is going to be the x component of the force times the distance that we drag this thing. The y component doesn't do any work, but the x component does. And that's basically f sub x is just equal to f times the cosine of theta. So it's the same kind of deal. It's just a little fancier way of doing it. But the interesting thing is, one thing about dot products, this will be the last thing we talk about, is that if you have two vectors in space, let's say we have, so these are two vectors, and let's say this vector is, here's the origin, and let's say this is 6 units in the x direction and 6 units in the y direction. And this vector is maybe 2, no, it's more in the x direction. So let's say it is 12 in the x direction, but only 2 in the y direction. So those are our two vectors. Again, we can show let's say this is vector A, and this is vector B. So these vectors you can represent. So vector A can be represented as a coordinate pair. And we use these little brackets that look kind of like greater than, equal, greater than, less than sign. Vector B would be the same thing, except with 12 and 2. Or we can write it as 6i hat plus 6j hat. So we could say it's an x component and a y component. Same way here, it's 12i plus 2j. Now the interesting thing is that if I wanted to find this angle theta between these two vectors, how would I do it? Well, one way is you could make two right triangles, and then you could find this angle, and you could find this big angle, and then subtract them. But it turns out that if you have two vectors, A dot B, using the dot product, it's equal to the magnitude of A, which is a length, the magnitude of B times the cosine of the angle theta between them. So let's do the calc. So then if you want to solve for the angle between them, or the cosine of the angle, it's going to be the dot product of the two vectors divided by the magnitude of the two vectors. So the magnitude of vector A is just equal to the square root of 6 squared plus 6 squared, just using the Pythagorean theorem. So let me get my calculator out. Must have it somewhere here. Maybe it's in my other bag. Oh, here it is. Okay, so you take 36 plus 36, take the square root, and we get 8.48 units. And the length of vector B is equal to the square root of 12 squared plus 2 squared. So that's 144 plus 4, and then you take the square root, which is 12.17. Okay, so that's those two parts. The dot product of two vectors. So let's write the two vectors. One is 6, 6, and we dot that with 12, 2. all we have to do is just multiply the components together. And this is a vector dotted with a vector gives us a scalar, which is just a number. So this will become 6 times 12, which is this times that, plus the second group, which is 6 times 12. So that's 72 plus 72 is 144. So the scalar associated with the dot product is that. So it says that the cosine of the angle between the two vectors is 144 divided by 8.48 times 12.17. So 144 divided by 8.48 divided by 12.17 is okay, something's wrong. I'm getting a number greater than 1, so obviously something is wrong. So what did that do wrong here? Okay, let's go back to our definition. Cosine theta that looks right. That looks right. Just check the equation. Okay, I found the error. Hopefully, maybe you did too. I should have multiplied that by 2, not 12. So we get 72 plus 12, which is 84. So this becomes 84 instead. So 84 divided by 8.48 divided by 12.17 is 0.814. And so then if we take the inverse cosine of 0.814, I know it was wrong because it had to be between -1 and +1. So take the inverse cosine, make sure my mode is correct, which I don't have it in the right mode. So inverse cosine of 0.814 is 35.5 degrees. And that's the angle between the two vectors right here. Now let's just go ahead and prove that that's true, doing what we were saying earlier. If we break this one up into two, a horizontal part, and then we take the second one and we break it up into horizontal and vertical parts. And let's call this call this angle here alpha, and call the big angle here beta. So we have the two sides of a triangle. So we could say that the tangent of alpha, which is this angle here, is going to be 2/12. And we could say that the tangent of beta is 6/6. So alpha is going to be the inverse tangent of, we could simplify that down to 1/6. So take inverse tangent of 1/6 and you get 9.46. So alpha equals 9.46 degrees. And here you take the inverse tangent of 6 divided by 6, which is 45 degrees. So theta would be equal to beta minus alpha. So if you take the whole angle and you subtract alpha, that leaves theta, and you get 45 minus 9.46. 45 minus 9.46, and you get 35.5 degrees. 35.5 degrees is theta. So that's how you do it using the geometry using components, and using the dot product, we came with the same answer, 35.5 degrees. The other way of doing it, which would be even more complicated, and we don't do it that way, is if you were to take these two vectors. Come over here. And if you created a not a right triangle, but it's a triangle with this. And so this length here is going to be, what's the length of that side? 8.48. 8.48. This one was 12.17. And what else do we know? What I try to think is use the law of sine and this is the law of cosines. So we have two sides. We're trying to figure out what this angle is, which is theta. So yeah, I'm not exactly sure how you do that. Anyway, there's even more complicated way, which I'm not going to worry about. But the simplest way is to use the dot product. If you have two vectors that you're trying to find the angle between, because if we come back to this equation, not this one, but we come back to here, if we have, this one's easy because the dx is in the positive x direction, so it simplifies down. But if the force were in this direction and the displacement were in this direction, say you're on a ramp, how would you do that? Well, it would be a lot easier to find the, if you wanted to find the angle between the two, it would be a lot easier to do the dot product and use this result. It's fairly mindless. You know, you have the two vectors, you do that product, you find the magnitude, and you just plug it in there and you get an answer. So that's when you get to more complicated two-dimensional and three-dimensional problems involving forces and displacements in terms of work, then you have to worry about that. Now, you know, if you're taking statics as a class, you don't actually ever have any displacements. You're only worried about, you're still worried about the angle between the two, between vectors, but you wouldn't necessarily use this fact. You wouldn't calculate work in a statics class. You would use it in a maybe a dynamics class, which is what the next class you would take as an engineer.